Good afternoon, everyone. So, what's up? How are you all doing? Doing all right?
Yeah.
Okay, good. Did you get a chance to look at the homework? I know I just posted it a day back, but just checking with you.
Yeah.
Let me share a screen. My screen with you. So, yeah, the first question is, you need to, it's about what is the FPGA you are using on the Amazon F1 instance, and what are its properties? Okay, how many LUTs it has, flip-flops, DSPs. So anytime when you're working with an FPGA, this essential information you need to know. And similarly, what is the host machine's configuration, how powerful it is. Because when you are designing an application, especially when you look at F1 instance, it's we call it as we are doing the computations at the server or the data center. We are doing the computations on the data center. So on the data center setting, usually an FPGA could be connected with a powerful host system. So you should be able to split your computations between the host and the FPGA as per your application needs. And this is what is called as heterogeneous computing. Okay, so I just want to again remind few things to you. First thing is, so when we think of FPGA usage, there are two things we should, there are two use cases. One is embedded system. The other is a data center or a server side data center. The setting that we have here on Amazon F1 instances, it is the data center setting. So you have a powerful CPU connected and the FPGA connected through a PCIe bus. Okay, this is the setting. And you may have noticed that in the particular F1 instance that we are working with, we have only one FPGA, but there are other instances where two FPGAs are connected to the CPU or via PCI Express bus, or four FPGAs are connected to the CPU via PCI Express bus. So you can see that there are 1, 2, 4 FPGAs configurations available on the Amazon cloud. Apparently, for us, we are given permission to use only F1 instances with only one FPGA. We are not given permission to use F1 instances with 2 FPGAs or 4 FPGAs. So, yeah, please check all this information. And the other thing is this one, this setting, we kind of call it as heterogeneous computing. where we can use the full power of the CPU, because if you see, the CPU also has 8 cores on it, vCPUs. So the CPU and also the RAM available on CPU is also very large. So you can really know, so it's when some computation is happening on FPGA, in a real application, you may want to use the CPU also to do some kind of computation. Okay, so keep that in mind. Heterogeneous computing. Second is the embedded system thing, where no, that the multi.
Sir,
Yeah.
sorry to interrupt.
No
So
problem.
this first question, we only need to write about the FPGA F1 instance, right? Or the whole setup, how it is, and all the stuff.
Not necessary. We can just write
Okay.
that. Yeah, that's
Okay.
okay. Second is in the embedded systems space. Usually, the FPGA programmable logic and this programmable system, the CPU and FPGA, they are closely tied within the same chip, so to speak, if I'm right. So PL stands for programmable logic, where we can kind of whatever the custom circuit you can keep there, and PS stands for the processor. Usually ARM processors are present. If you look at Xilinx boards such as ZC102, or I may not have got these numbers right, but yeah. So there are embedded systems boards where the programmable logic and programmable system, this processor, they are on the same die. Yeah, I guess so. And so there is the communication between PL and PS happens through some AXI interconnect, AXI bus interconnect, AXI. Okay. So this is the embedded system space. But here in embedded system space, the processors, they are reasonably powerful, but nowhere comparable to what you get in the data center setting. You may have a dual core ARM processor running here, or perhaps quad core ARM processor running, depending upon what embedded system FPGA you are looking at. So keep this in mind. Any questions here? Okay. So I hope you're all doing good then. So this is about first question. Second question is, so what is the PCI bandwidth to the FPGA device on the F1 instance? So I think you can use this command xbutil and try out different options and see how we can what is the available PCI bandwidth from the CPU. And question 3, yeah, so we have already seen the VAD and wide_VAD programs. They are available on the GitHub repo. You just have to go through them. Okay, so for different vector sizes, how measure these things, try to the questions I kind of kept it rough, but my intention is for you to kind of do an analysis as you do this homework. Okay, don't just do the homework for the sake of homework's sake. So try to see what is happening. If there is something interesting you can find out, you can make a comment about it in the report that you submit. So for all these things, I expect for homework 1, what you have to submit is a report. Okay, and for question 5, you need to submit the code also. Okay, so for question, so expected thing is there's a report, but questions 1 to 4, you don't need to submit the code. But question 5, you also need to submit the code. The submission instructions I will give in some time. Okay. Okay. Yeah. All right then. So this is about homework. So yesterday in the office hours, I got a couple of questions I would like to answer them now. So yeah, let me share my whole desktop. So this is the homework which I asked you to do at the beginning of the couple of few weeks back. So far, if you see in this one, IIITH intro 1, I'm sure by this time you should have finished this IIITH intro 1. And then in IIITH intro 1, you just do software emulation. And in IIITH intro 2, you do hardware emulation. And after that, after you do hardware emulation, at some point, so you run, you do build and run hardware emulation. You do this and then you use IIITH analyzer and see what is happening. Let's keep going down. Yeah. So here, you should, from this step onwards, some of you yesterday asked, what should we do here? So here, you should actually set this active build configuration to hardware and just go ahead and build the hardware. Okay, you should go ahead and build the hardware. It may take some 90 minutes for the hardware to build. And after the hardware is built, so you will get this file, XCL bin file. Okay. So usually, let's say there is your host. I don't know how many of you by this time realized. So we have looked at this example. So let's say from your source code, 2 files get, let me change. So from your source code, so whatever from your source code, 2 files gets generated. So one file is like, for example, the host program, VAD. Okay, this is the program. This is the executable which runs in on the host. So if it is a, like, for example, if you compile this program on a Windows machine, this may have .exe extension, because in Windows, all executable files have .exe extension, but not in Linux. Okay. In Linux, you may just have the VAD file, and this code runs on the host. Okay. And then, I forgot the exact file name that gets generated, but for the sake of, but what you get here is XCL bin file gets generated. And this is the file that will be used to configure the FPGA. So when you give your program for execution, you give VAD this file name. Okay. And if you observe the source code, you will see that at some point, you use this file to flash the FPGA. This is what happens. This is the execution process. VAD executes on the host, and this file is used to configure the FPGA. But in the case of, this is the usual thing. But if you are using, but if you are using, but on AWS, what we have to do is, we have to use something. You have to create an AFI. There is some script we will see. So I think something like create YTs_AFI or something like that. And then you give this XCL bin file. And then what happens is this XCL bin file it gets transformed into, so the prefix here will not be VAD. I just used VAD. It will be something. It gets transformed into AWS XCL bin. It gets transformed into AWS XCL bin. So all these steps you do using the M2 instance that you are working with. Okay, using the M2 instance you are working with. And after this file gets executed, you stop the instance. You stop the instance and then change the instance type to F1. Instance type to F1 instance. And then you give the command VAD and then you start the machine, and then you have VAD.AWS XCL. So this is how you run the program. So till this step, till the AFI creation, you run it on your usual instance, and after the AFI gets created, you go and we changed F1 instance and then execute this. So in order to, it is binary underscore container underscore dot. Okay, good. So I just want to check, did anyone try to run the FPGA so far, run the programs on the FPGA? Can I see a raise of hands? Did anyone try to run the programs on the FPGA? You should be active and try to do things. Great, I see at least few students. Harsha, Tanmay, very good. Aditya tried it. Great. So if you let me again share a different screen. So if you see the instructions here on this IIITH intro 2, if you go down to the end, you will see, so test on AWS create AFI. Okay. Once the full system is built, that is, once you build the hardware, you can create an AFI by following the steps listed in create an AFI. You go here and you follow the steps. Okay. So in these steps, one thing you need to, if you recall in the first, in the video, in the demo video given by Mr. Parimal, so we did something called as AWS configure, and before we did the AWS configure, we changed in the .aws credentials file, which we have to put the appropriate credentials in it. So it looks like every time we log in, this credentials file needs to be updated. Okay, because I couldn't, when I tried to just do configure without updating the credentials file, I got some error. So perhaps when you log in, you update this credentials file. This is step 1, and step 2 is do AWS configure. And after you do that, you have to execute this command. Okay, you have already, if you followed the steps before, you already have an S3 bucket, you already created a DCP folder, you already created a logs folder, and so you have to execute this command. This is step 3. So step 1 is credentials change. In the console, the credentials that you see, you go to, when you log in, you change this credentials file. Step 2 is you run the AWS configure. Step 3 is you run this create underscore IIITH underscore AFI script. This is the 3rd step. And so after you So after, let me see. Okay, that is the third step. And yeah, this is also important. The fourth step, the third step is somewhere, let me write down the third step here. Eraser. So the third step is create underscore whiteis underscore AFI is the third step. And the fourth step is you run this command, okay? You check the AFI status, create, describe. So it will be, so initially when you, as soon as you give this command, and when you do it, initially the status will be pending. And I think, so around half an hour after, it takes around half an hour and pending. And after half an hour, it gets changed to available. And so you can log off from your machine and stop the machine, but we don't need to log in for the status to change from pending to available. But before you actually change, and step 5 is, let's say step 5 is stop M2 instance. Step 6 is change M2 to F1 instance in the EC2 dashboard. This we do in the EC2 dashboard. And step 7 is actually start F1 instance, start the machine. And step 8 is execute. That is, you give vadd followed by whatever that bin file. Okay, so these are the steps that you need to follow in order to execute your program on the F1 instance. So by Saturday, I hope that you do all these steps. And if you have any problems in this, you should get back to me and let me know. Okay, so I can possibly have a separate session for those of you who are having for those of you who are having problems, I can help you out. Okay. So perhaps I can even ask, so Aditya?
Yes, sir.
Yeah, so is it possible for you to kind of take a half-an-hour session or something like that to help those students who have any trouble on Friday evening or something like that?
Sure, sir. Fine.
Yeah.
Friday, actually, I don't have office, so I can connect to anyone who
Then
is
if you
free.
can let a convenient time for you, then I will post it with all the Zoom link, etc. So that those students who have any trouble, they can take your help and get it fixed. Okay.
Sure, no problem.
Okay. Awesome. Okay, so the other thing is, so even if you are not, even if you stop your instance, you will see few credits going down for that is because you are using storage on Amazon. So that is all right. So over a period of next couple of months, as the course, which is the course duration, at most $10 to $15 may go for storage cost. The rest of the $85 or $80, you still have, you will still be having for the compute. So that should not be an issue for you. Okay. Are you hearing a lot of background noise? It's heavily raining here, so.
No, sir.
just give me a minute. All right then. So now, what we will see, we will continue our discussion from last class, and yeah, and see what we can learn. So before we start the discussion, so if you see this sheet, collab sheet, if you check your, in on FPGAs, we use DSPs, while LUTs are also used for doing the computations. Especially they give the reconfigurability. DSPs are very, these DSP units, they do floating point multiplications and additions, fixed point multiplication and additions. They are very critical resources on the FPGA. So on the F1 instance, if you go and see the number of DSPs present in the F1 instance is 6,800. Okay, 6,800 DSPs are present. And if the DRAM bandwidth, it turns out that the DRAM bandwidth can, that is the bandwidth between the FPGA and the device memory on the FPGA, not the on-chip FPGA memory, which is BRAM, block RAM, but the external memory. So FPGA is there, and then there is a DRAM. We have seen, right, DDR0, DDR1, etc. Its bandwidth can go between 16 to 64, and but 16 gigabytes per second is depending upon whether it is the 32 GBP, gigabytes per second, or whether it is 64 gigabytes per second, depends on some other parameters like what is the frequency at which the DDR controller is working, things like that, etc. But let's say if the DRAM bandwidth is 16 gigabytes per second, and if the frequency at which your processor is running is 200, your FPGA logic is running at 200 megahertz, 1 megahertz is equal to 200,000 nanoseconds. So if the clock frequency is 200, then that means, it's like each clock pulse width is 200 times 1000 nanoseconds. It turns out to be 5 nanoseconds. The clock pulse width, if you are running your system at the frequency at which your FPGA is operating, if it is 200 megahertz, then the clock period is 5 nanoseconds. Just remember these two lines. This is so that whenever and if it is running at 300 the frequency, if you are running at 500 megahertz, then the clock period will be 1000 by 500. It will be 2 nanoseconds. Okay. So remember this tip that 1 megahertz is equal to 1000 nanoseconds. Then if you see the number of operations performed per clock cycle, per second, the number of floating point operations performed per second, it turns out to be, this is equal to the number of so if you see the gigaops you see here, it is the number of DSPs present times the clock period length, like 5 nanoseconds is the clock period length. But 1 nanosecond and 1 second is equal to 10 power 9 nanoseconds. So we are converting the nanoseconds to seconds. So this 10 power 9 is coming. No, this 10 power 9 is coming because we are 1 second contains 10 power 9 nanoseconds. So the numerator here, which is marked, it tells the number of computations that we are doing per second. Number of computations that we are doing per second, the numerator. And using the available DSPs, we are not considering here the computations that we can potentially do using the available LUTs, flip-flops, etc. So the numerator here is what the computations that we are able to do using the available DSPs. And we are dividing it by 10 power 9 because 1 gigaop means 10 power 9 operations is equal to 1 gigaop. So because of that, since we want to get it in gigaops, we are dividing it by 10 power 9. So overall, if you run this small chunk of code on this collab nodes, you will see that the clock period, if your FPGA is running at 200 meg, which it could be the typical speed, the clock period is 5 nanoseconds, and the gig operations that we can, floating point operations that we can perform is 34,000 operations per second. That is 34 teraops. If you see, it may not be exactly 34 ops because 34 teraops. It could be maybe between 20 to 25 teraops due to a variety of other factors. We may not exactly be able to get this level of peak compute power, but you can possibly safely assume, this is a very rough estimate. I may have missed the kind of ignore some things, but this is a good upper bound to have. Perhaps 20 teraops, teraflops, T-flops is not a overestimate. This could be your using your FPGA. This could be a reasonable number of operations you can do per second. Okay, which is quite big, 20 teraflops.
Sir?
Yeah.
Here, why we are taking the DSPs as the in the competition of the GOPS?
Because every DSP, if you want to do floating point operations, primarily we use DSPs. And so if you have 100 DSPs, you will be able to do 100 floating point operations per clock cycle, or depending, in a steady state. If you are able to use the DSPs in a pipeline fashion, perhaps, then we might be able to perform 100 floating point operations per second.
Okay.
So I will take a pause here and check. Okay, so any questions here? You're all, do you understand the reasoning here? When you look at the DSPs in the system, it gives us a good idea about how many operations you will be able to, peak operations you will be able to do in a clock cycle, in per second or something like that. Okay.
So their op intensity, it is taken as 1, right?
Well, ignore the top intensity. So there is no op intensity per se here. Op intensity is a function of the application.
Okay.
Okay, so it's a function of application. And we are not even using the DRAM bandwidth in estimating this upper bound. We can even take it, you can. So here, if you see, all we are doing is what is the number of DSPs that are available. And if you are able to use all these DSPs, then and if your system is running at 200 meg speed, then what is the peak performance that you can get is what we are looking at here. Okay.
Okay.
So here, one interesting design point that I would like to bring about here. So here, your original system, 6,800 DSPs is what you have available in your FPGA. There are two architectural designs. Okay, one architectural design uses some out of the 6,800 DSPs, one architectural design is able to use N1 DSPs, and another architectural design is able to use N2 DSPs. Like for example, we have seen with and without unrolling. Okay, so if you have a loop and if you unroll the loop, you get to use some number of DSPs. And if you unroll it by a factor of 8, you get to use some number of DSPs. And if you unroll it by 32, you get to use some number of DSPs, so on and so forth. I'm just taking it as an example. So there is one design, let's call this as design D1, and this is design D2. So one design is using N1 DSPs and another design is using N2 DSPs. And one design is using, C1 it is running at clock speed C1, and another design is running at clock speed C2. And if you see between these two, just usually what happens, we may think if C1 is greater than C2, then C1 is a better design. Okay, if C1 could be 300 and C2 could be C1 and C2 could be 150. So yeah, so you may think that C1 the design D1 could be better than design C2. But if you see the flops that we are able to use here is C1. If C1 is the clock, let me use instead of C1, I will use F1. Okay, this is F1 and this is F2. So if F1 is greater than F2, then we think F1 is better. Okay. But we know that, but this depends, we need to look at the number of operations, the number of flops, T-flops count. If you see T-flops count, okay, so if you look at what is the T-flops, what is the formula for T-flops count here? For this, what will it be? We are using N1 DSPs. So N1 into clock period length. Okay, clock period length, if F1 is given in megahertz, then so anyway, I think there will be some constant factors there, but it will be N1 by F1. This will be proportional to T-flops is proportional to N1 by F1, and this is proportional to N2 by F2. So what we have to compare is whether this is better or this is better. So we have to compare this ratio. So if between these two designs, which one is better, whether design D1 is better or design D2 is better, it depends on whether how these ratios compare with each other. Okay. Does it make sense? Like for example, if let's say if you take let's take this example, in design D1 is using 1000 DSPs and it is running at a clock frequency 200, and this is design D1, and design D2 it is using 2000 DSPs. Okay, but it is running at a clock frequency 100. Okay, So if you see this one, this is kind of some 5 units to get, and this is some 2 units. The ratio, if you see, then design D1 to D1 is to D2 if you take. So design D1 is better, okay, when compared to design D2. Okay. Oh, this is not 2, no, this is 20. Yes, you're all sleeping. This is
Denominator should be 1000.
denominator. No, let's say this is denominator cannot be 1000 because denominator is frequency.
Yeah.
Yeah. So this is if it is 100 meg, it is running, but if it is using 2000 CPI, DSPs, then this is how it is looking like. Okay. But in any case, you get the idea, right? So when we are trying to evaluate the design, there are 2 things that you need to consider. That is how well you are able to use the available DSPs. And second thing is the frequency at which you are able to operate. Usually what may happen is if you really want to use all the available DSPs, the amount of LUTs, the amount of flip-flops that you have to use, etc., could increase, and then the routing delays, the signal delays could become larger, and you may not be able to synthesize your designs at higher frequency. In fact, I heard through experience in our lab that it's very, very difficult to use 6800 DSPs. The design wouldn't converge. Placement and routing cannot happen when you put all the DSPs to use. Maybe around 4000 DSPs or 5000 DSPs we can use easily. But putting all 6000 plus DSPs, when you use the amount of other resources, FPGA resources that we use, will be very large, and we will get into some issues. Okay, take a pause. Any questions? Can we not just use the throughput to compare? So Tanmay, that's what we are trying to do. We are trying to compare the throughput. That is number of flops per second is the throughput, and in order to get that throughput, you need to multiply the DSPs utilized into the clock period length, right? So that's okay. So yeah, flops. Is there anything wrong in the computations that I did here? Just want to check. Is it N1 by F1, or can we try to rework this? Because I have a doubt here. Is there do you see anything wrong in the computations that we are doing?
Sir, here N1 by F1 will make us not in per second, it will make seconds the metric.
Yeah, so that is what in the code also it is showing, right? So F is something and you have clock, which is 1 by F, and then you multiply with DSP, so it is N1 by F1. So that's what it is we are trying to see here, I guess.
But but per second, it's not per second, it will be seconds.
Yeah, there is, let me do one thing. There is something wrong here. Yeah, I'm sorry, guys. Let's see. So we have design D1. So design D1, it uses N1 DSPs, and it runs at frequency F1. So if it runs at frequency F1 and design D2, let's fix this. I think there is a bug in my argument. So it uses N2 DSPs and it runs at F2 frequency. Then the number of clock pulses per cycle will be what? How many clock, the DS per second clock pulses number of clock pulses per second. How many it will be if the frequency is this?
So it will be F1 only, right? So
It
that's
will be F1 only, right? Yeah, that's
Yeah.
the so this will be F1. So here also, if you take the same thing, it will be F2, the number of clock pulses per second. So the T-flops count, T-flops, yeah. So T-flops count is equal to N1 F1 here, and it is N2 F2 here, which makes sense because if the frequency is higher, then you should be able to do more number of computations per second. So similarly here, this will be N2 F2. This is the mistake that I did there. It's not N1 by F1. This is N1 F1 and N2 F2. Is this all right? Does this make sense? You all agree with me? How many of you agree with this thing? Because we did a mistake before. So okay. Great. Okay. So now let's come back. Share. I hope we are good here. This one. So here 2000 roughly.
Excuse me, sir.
Yeah.
So in the frequency, it is written 200, and what is the unit of the frequency? MGhertz.
Yeah,
Like is it gigahertz or megahertz?
Megahertz. Megahertz. Yeah. I think maybe that G should not be there.
Okay.
Yeah. Yeah. Okay. So now let's come to the example that we are looking at in the last class and see how it goes. Okay. So this is going to be an interesting example. This is there in your homework problem also. So I would like you to pay attention to this example. Okay. So remember, so for an application, so if you take, there are few, so given for an application, in fact, so we have the thing, what we are interested is the operational intensity, OI. OI stands for operational intensity. And what is operational intensity? Which is nothing but operations per floating point operations, or let's say operations per byte. Per byte of data that is fetched. Okay. So this is operations per byte. OI stands for operational intensity. And so if the peak memory bandwidth, peak memory bandwidth is if it is equal to, so let's say let's represent it as, let's call it as MBW. So it can be something like, units will be something like 16 gigabytes per second or 8 gigabytes per second or something like that. And let's say this example, this is half. Then if the operations per byte is is half, that is for every 20 bytes of data that you do, that you bring, you are performing 10 operations. Then the ratio is 10 by 2, which is half. Then the possible attainable gigaflops per second is equal to operational intensity OI into memory bandwidth. But of course, what can happen is, let's say, if your system can perform, like for example, in this case, you can the attainable gigaflops per second is 8 gigaflops per second. But if your system can only, the raw compute power that is available on your system is 4 gigaflops, then that means you will not be able to achieve this peak. Okay, so because of that, so what we do is we write attainable memory gigaflops per second as minimum of peak FP performance comma OI into MBW. Are you all with me here? This is the first step. This is the first step. You all understand what is operational intensity is? Let's try to work this example through this. Let's try to work this out through the querying, through the problem that we have introduced in the last class. In the last class, we are looking at the Aadhaar card problem. We are looking at the Aadhaar card problem. So in the Aadhaar card problem, what happens is we take a fingerprint and we pass this fingerprint through a CNN, and we get a feature vector. We get a feature vector. F is a feature vector. And we store this, your Aadhaar card, your fingerprint is stored as a feature vector in the database. Okay. So let small v be the dimension of that. Let small v be the dimension of F. Like v can be 256, 500, 1000, whatever it may be. Let v be the dimension of F, the feature vector. So your database has n feature vectors, where n is the kind of population of India. Okay, think of the n is the population of India, and your whole database contains n feature vectors. So if you think of your this database, you can even think of your feature vector as an n by f matrix. Every row here corresponds to a citizen of India. Okay, corresponds to the fingerprint of the associated with the citizen of India. And now, given a new, so now when we go for registration or something, so they want to verify whether you are the right person by taking your feature vector. So query vector, we have a query vector Q. So you want to compare this Q by taking the dot product of Q with this. If there are two vectors, if you take the dot product of these two vectors, this is one vector V1 and this one vector is V2. The dot product of these two vectors, if the angle between them is 0, or if these two vectors are close to each other, it will be close to 1. And if they are separate, like for example, if V1 is orthogonal to V2, then the dot product is equal to 0. So you take the Q and take dot product of Q with all the vectors, and you check what is the closest vector to it. Okay, so that's the query vector. You want to find a vector in the database which is closest to Q by computing dot product. So this is the problem that we have. And if you take this problem, so what is the operational intensity? You first, you assume Q, you bring it to FPGA and store it in a register. So you can ignore the data transfer cost associated with query vector. You just think it's negligible. But then, so what you do is your query vector is on the FPGA register. You keep streaming the rows of the matrix. So you keep streaming the rows of the matrix. This is your n by f matrix. You first stream the first row, and then you stream the second row. You keep streaming the rows of the matrix, and you keep computing the dot product with the query vector. So if you see, every time we want to compute a dot product, there are, if you want to compute dot product between two vectors of size 100, you perform 99 multiplications and 99 additions. This is what is called as a multiply and accumulate. In dot product, we do multiply and accumulate. Multiply and accumulate. So why is this multiply and accumulate? Because you know sigma I is equal to 1 to n. If you do ai bi, if this is the dot product, if you write a loop, what happens? You do for I is equal to 0, I less than n plus I, dp sum dot product sum plus is equal to a of I into b of I. So you are doing this multiplication and then you are accumulating the sum in this variable, and these are called as MAC operations. And DSPs are very good at this MAC. In fact, DSPs are specially designed to do what are called as this floating point FMAC operations, floating point multiply and accumulate operations. Okay. So, but in any case, you get the idea that you perform one multiplication and one addition. So the operations that you do as a part of querying this is for every vector, we perform 2v. Remember, v is the dimension. This is for every dot product between the query vector and a row of this, you perform 2v operations. And since we have n such rows, we have n into 2v. And then, so n times 2v. And then what is the total data that is fetched? So we are fetching n into v into 4. N into where v is the 4 is there because the size of each vector element is 4 bytes. And you have to bring n rows. Each row is of is v dimensional and size of each element is 4. So the operational intensity is half. So the operational intensity is half. So now if you look at this example, so if the operational intensity is half, and so what is the peak and the DDR4 bandwidth? Let's say the DDR4, whatever the DDR bandwidth, the main memory bandwidth is 16 gigabytes per second. Then attainable T-flops, attainable gigaflops per second is 16 into half, which is 8 gigaflops. So on an F1 instance, if you solve this problem using this approach, you are able to get attainable gigaflops of 8 gigaflops. But whereas your F1 instance, it has 6,800 DSPs, and it can, in the best case, it looks like it can even achieve, some 32 teraflops per teraflops. And even if you kind of have a realistic estimate, it is 20 teraflops. And now you have 8 gigaflops. So it's like you're almost using only 1% of the available compute power which your system is using, which is just bad. Okay, which is just bad. So now the question for us is how we can improve this design.
Sir,
Yeah.
just one question. In this operational intensity, the numerator part, when you have n into 2v, so that 2v is like a number of, so the numerator is the number of operations, right? Yeah. So n into how the 2v, what's that? So if you have
v is the dimension of the vector. So in order, when you're performing the dot product of two, maybe it's better to use d rather than v.
So but means it's like V additions and V multiplications.
Yeah, that's true. That's true. V additions and D additions and demultiplications.
Okay.
Yeah, that's true. So the attainable gigaflops is just you are not using your FPGA at all. You're not using your FPGA at all. Like so that's sad. And in fact, if you see this whole operation, your query vector, it is a f/1 vector. So you are multiplying your matrix with the vector. This is a matrix vector multiplication problem. This is the matrix, this is the vector, and you are multiplying your matrix with the vector. The vector you are storing it in the, this is an f/1 vector. So this vector you are storing in the FPGA memory, and this matrix you are streaming. And the attainable gigaflops is ridiculously small. Okay. So this is a challenge. This is a challenge. So in order to kind of put your use in the application that we are looking at, in the Aadhaar card application, it is a kind of application where you may have a server where millions of people across India would be accessing that server, asking queries corresponding to their fingerprints. So at any time, we will never be short of query vectors. So what we can do is we can bunch the queries, like so batch queue queries, because we will never run out of the queries. So when we batch queries, then the problem looks like this. So you have a matrix. This is the database, and then you have an F/Q matrix. Okay, this is every column here is the query. Every column here, it's a query. Okay, this is what we are bunching the queries. You take this, like the first column is a query, the second column is a query, the third column is a query, and then so if you see when you stream in this first row of this matrix, you multiply this, take the dot product of this with the first column, second column, third column, so on and so forth. And so the first row of the product matrix gets rendered. The first row of the product matrix gets rendered. And then you stream in the second row, you take the dot product of this with each of these rows, and you store each of these things in a the corresponding multiplication. So you render the second row of the product matrix. So now let's say magically speaking, so somehow you are able to bring this whole query matrix and store it on FPGA. So let's say you store this query matrix on the BRAM memory of FPGA, you are not streaming it in. Somehow we do it magically. Let's assume if you are able to do it, then what happens is your operational intensity becomes, so every time you bring the number of computations that we do, so you bring this matrix and you perform this many operations, because n into 2d into q operations that you do, because you are not only taking the dot product of this first row with the first column, you are taking the dot product with these q columns. So the operations gets multiplied by q. And in the denominator, the data that you are bringing is still the same, n into d into 4. So now the operational intensity becomes q over 2, q over 2. So earlier in the peak, if T1 in the previous design, T1, that is peak attainable compute, the flops per second, it is 8 gigaflops per second. But let's say if this Q is, if it is equal to 1000, for example, then if Q is equal to 1000, if Q is equal to 1000, then T2 becomes 8 teraflops per second. Okay, 8000 gigaflops per second, but now it becomes 8 teraflops per second. Are you all with me on this one, or lost? Doing all right? Can I see a raise of hands on how you are doing? Okay, this example is extremely important example. I cannot emphasize enough that this is a simple example, but we still understand quite a bit through this example. Okay, great. So, but there is one interesting thing that we need to, there are a couple of things you should understand here. In order for you to be able to use, to multiply in order for you to be able to achieve this many gigaflops per second, it depends on if all these query, so in your memory on the FPGA, your DRAM consists of a number of blocks. Like for example, on the on the Amazon F1 instance, so your total DRAM size, is equal to 76 MB, and but this DRAM is distributed into a number of DRAM blocks. Okay, DRAM blocks, and the number of DRAM blocks is equal to something like 2160. Yeah, there are 2160 DRAM blocks. So what it means is, in order for you to be able to perform this, in this example, we are kind of thinking that, so what happens is, what is a DRAM block, DRAM memory block, memory roofline? Now it becomes a DRAM memory roofline. Okay, so you should be able to read this 2160. The maximum number of reads that you can do is 2160, because or each of these DRAMs, they are kind of dual ported memories. So you might be able to read 2 data items per second, or how you organize these DRAMs, it dictates what is the available DRAM bandwidth for you. Okay, so what we have to do is, like for example, if you see each of these query vectors, you may want to place each of these query vectors in a different DRAM block. Okay, so that way the dot product between this F and the first column and the dot product between this and the second column, so on and so forth, all of that can happen in parallel. Even then also it may not happen in parallel, because if all these so let's say if this is present in Q DRAM blocks, then at most Q multiplications and additions you can do per second. But whereas if you can see, the true potential that is available is F times Q, because you can take this F and then multiply it with any of these elements. So if you are able to spread this whole FQ, F times Q, FQ elements into separate registers or organize them in some way, you might be able to perform all the operations in parallel. But even when you do it, you get into some other issues like because you have to accumulate all the sums that are there, so that correspond when you multiply this and this. If you do complete parallel multiplication, then you have to use some other kind of tree adder structure to do the sum accumulation. But anyway, let's keep that aside. But the important point, at least I would like you to make a note here, is in order for you to be, while these Q queries vectors that are there, if you can place each of these queries in a different VRAM block, then that would be the best for you. So that way you will get maximum VRAM bandwidth that is available, and you can, that way you will be able to do as many multiplication operations as possible in a single cycle and put DSPs to good use. Like for example, at least in this case, we are assured that if Q can be, there are 2160 VRAM blocks, so we might be able to process Q queries in parallel. Every query is present in a VRAM block, and what you can do is in every clock cycle we can put to use at least 2160 DSPs. So if the peak attainable teraflops is 20 teraflops, by using this approach, we will be getting at least 7 to 8 teraflops per second by using this approach. Okay. Are you all with me here? You understand this? So many interesting ideas are emerging here. I want you all to kind of get some intuition about what is happening here. So in HLS, when you try to do these things, you have to use the pragmas and tell the HLS on how you would like to store this query matrix. Okay, how you would like to store this query matrix? You should tell the HLS by using some pragmas. Okay, hey, partition, because this is a two-dimensional array, right? So this two-dimensional array, how would you would like to partition it and store it on the VRAM? You should tell HLS. So that way HLS does this matrix partitioning appropriately, so that you get the best parallelism out for this design. Okay, are you doing good on this one? Again, can I see a raise of hands on? Does it make sense what I'm talking? Yes, no, maybe. Just 1 minute. Okay, someone, okay, good. Nice. So now I would like to, so earlier we thought magically we will have this query vector, this query matrix in the memory. But then in practice, there is no magic. Okay, so how will you bring this query matrix to the memory? Earlier, when we were thinking of only one vector, we thought, hey, let's assume it's negligible time and no, don't worry about it. But when we are thinking about a big query matrix, the time is no longer negligible. So what we have to do in order to solve this problem is, which is a very important technique which is used, is if you have your core, this is your whole compute block. This is your whole compute block. What we do is this compute block is fed by two buffers. So this is in1 and in2. In1 and in2, sorry. In1 and in2. So when your compute block is processing in1, when this compute block is processing in1, so this there will be you will have one more read block, mem read block. Mem read drawings are pretty bad, but I have to live with it. So memory read block. So this memory read block, it accesses the DRAM. This is your DRAM. So initially what it does is this has access to both these blocks. So what the compute block does is memory read block initially fills in this in1 block, and compute block does the computations on in1. As the compute block is doing computations on in1, the memory read block in parallel fills in in2. So after compute blocks processes in1 buffer, it switches to in2 buffer, and yeah, and while it is working on in2 buffer, the memory block fills in in1 block. This technique is called as a double buffering technique. Double buffering technique, double buffering, or ping pong. So here, what is the size of this in1? Okay, so what is happening is there is a time taken to fill this in1. Let's say time taken to fill this this in1 is, let's call the time as tm, and which is a function of q, that is the number of, in this particular case, the number of query vectors that we are working with. And there is a time taken to compute this thing, TCQ. This is the time taken by the compute block to process a bunch of Q queries, and this is that the time taken to for the in1 for the memory block to read data from the memory to this. So we would like this thing if TMQ is very, very greater than, it is greater than, let me, if this time is greater than, quite greater than, this greater than is not bit shift operation, that is, if it is quite big than TCQ, then most of your time your compute block will be waiting for the data to arrive at. Okay, so this is not a good design, memory bound. Okay, you are waiting, your compute block is all the time waiting. Okay, and if TMQ is less than or equal to TCQ, then it is good, because then what happens is you are able to hide the communication latency. So you will get a very good compute communication overlap if this is the case. To participate, yeah. So please unmute yourselves and ask. Question? I saw a couple of you raising hands. Okay. So if there are no questions, let's continue. So similarly here, in the out1 also we have the same story. So we have out1 and we have out2. So, and then what happens is, and then there is a, so there is a block, mem write block. So mem write block, which writes to DRAM. So the way it works is, let's say in1 processes, compute block processes in1 and writes it to out1. So And then as this is happening, of course, in2 is getting filled up. And once it processes in1, so compute block, instead of writing to out1, it will write to out2. And as it is writing to out2, this out1 will be written to the by the memrite block to the DRAM. Okay, so again, double buffering is happening at the output end side. And this particular approach is this particular architectural approach is quite common to many problems that we solve. Okay, so there is a double buffer at the input side, and there is a double buffer at the output side. And the key thing for you, in order when you try to decide what should be the size of in1, into, out1, out2, in this particular case, Q is the number of queries that we would like to batch. And this story, so this depends on, so we would like this thing to kind of, we would like to hide the communication latency. Remember I said, no, let's think that magically we are able to bring the query matrix to the FPGA. So how do we, what is the magic? The magic is we want to hide the communication latency by overlapping it with the compute. Okay. So this is the big picture, guys. This is the big picture. The ideas that we have seen in today's class are very important. So we studied matrix vector multiplication problem. We studied matrix multiplication problem. Here we assumed that this F, this F is small enough to be able to present in the VRAM. But what if this F is really large? So some other questions are there. And some important, yeah. So here, let's go back here. So in the design of these buffers in1 and in2 are very important, because if this in1 is like the way it is drawn, it is looking like a queue, but this in1, you want to have this in1 divided into multiple partitions, and each partition is allocated to a separate VRAM block. So that way the compute block will get maximum bandwidth from this buffer. These VRAM blocks, if it has 2000 read ports, then the compute block will be able to do 2000 parallel reads and be able to perform 2000 multiplications or additions. So this in1 and in2 and this out1 and out2, all these, similarly, when you are generating 1000 outputs, and if your output buffer has only one write port, then it will be a trouble. So you need to again use this output buffers also. You need to split them into multiple blocks so that we can do parallel writes. So here it is essential to have parallel reads. Organize your memory so that you can have parallel reads, and you would like to organize your memory so that you can have parallel writes. Okay. And what is it that prevents you to have put a limit on the parallel reads or writes is the number of VRAM blocks that are available on your FPGA. Okay, so just putting it in a different color. Yeah, I see, Aditya. Just give me a minute. I'll take your question. Okay. Okay, Aditya, let's go. Go ahead. Have a question?
Sir, I have one question.
Yeah.
So can you go to the previous slide, previous figure?
Okay.
Here, when you said that Q is another matrix, for example, so you have Q queries, but when you said that Aadhaar card problem, whatever we have, so there the problem would be like the real-time scenario where one person comes and put his fingerprint or something. That will be only one feature vector, because there will be one person which you are trying to query for the whole database, right? But in what case there will be Q queries, which will be like Q queries means there will be Q people which should be queried at once. So what is that?
No, that is you are assuming that the other database is locally present there. But if you have a server cloud, you just take the fingerprint and you go to the cloud, and from the cloud you get the response back. So if it is a cloud, like for the whole of Telangana state, you may have one data center to which all the queries are coming in.
But my question is, what is the use case where you will have more query vectors to be queried at the same point? Because there will be only one feature vector when you are trying to query one person, right?
No, that's what Aditya, if there are, for the whole of Telangana state, there is one data center and there are different terminals which are accessing that where queries are getting streamed to the data center. There are thousands of people who are asking, queries are getting generated, right?
Okay.
Yeah.
Got it.
If the case where if it is a local machine one, then what you said is perfectly right. It doesn't make sense. Okay.
Yeah, got it.
So you have to see, actually, it's a good question. So depending upon the application, sometimes, in this problem occurs, the question which Aditya posed, in many CNNs, in object recognition tasks, etc., you have a feature vector followed by an FC layer. And the FC layer computations are very memory bound. So what happens is, if you just work with one memory bound thing, you don't get, if you have only one vector, then it doesn't, the FC layer on FPGA doesn't quite work. So people usually say, yeah, there's a stream of videos coming and stream of frames coming, and we group the queries together and do this something. So it sometimes in some application context it makes sense, in some other application context it may not make sense. But here in this particular case, if you take the Aadhaar card example and the particular data center scenario that we looked at, it makes sense. Okay, and that's how we are able to get peak performance. Okay, so Aditya Gupta, so you have raised your hand for quite some time.
Sir, that's my mistake. Sorry, I didn't notice it.
Okay, then. So if I want you to think about the discussion in today's class, because this is a very foundational or fundamental class, last class and this class, where we use analytical approaches to drive our design. So in hardware, there's a space of hardware design is very large, whether Q should be 20, 30, 40, 100, it depends on the FPGA, it depends on F, it depends on so many things. Given a problem, we should need to be able to build some kind of model for the problem, and then use that model to choose the appropriate parameters, so that we get the best performance out for our design. So in the absence of this design, in the absence of this approach, you are like shooting in the dark. You don't have any idea. You try something, you get some performance. You try something else, you get some other performance. But what is the bottleneck? Is memory bottleneck? Is compute bottleneck? Or is there more potential for improvement? And remember, these things are not that easy to kind of explore by running it, because every time you have to do a hardware compilation, you take 2 hours, 3 hours, 4 hours of time. So you cannot just keep on doing or give a hit and trial. It's not going to work. Okay. At least you should reduce your space of possibilities from 1,000 to maybe a few tens. Then you can possibly try them out by synthesizing the designs and how they are performing. In the absence of that, just blindly doing it is not going to help you. Okay, then. So I will stop here. So request you all to think about the discussion that we had in the class multiple times. Make sure that you understand what's going on, and yeah, so we'll catch up next class. Thank you.